So I just want to give a summary of what we saw last time or yesterday. So for the people who didn't understand or if I was not clear. So we try to classify the value of the dark matter mass m in terms of the two properties. First of all, the occupation number and occupation, which is basically the number of particles per W volume. And basically, we said that if m is larger than around 30 eV in the dark matter in our galaxy, will have an occupation number much more than 1, meaning that there are not many particles per W volume. Maybe there is only, well, there's actually much more than 1. And in this regime, the particles behave like single particle, very separated from each other, very localized, and this is the case of WIMPs, for instance. So you have to imagine the particle wave function is very localized in space. And in this case, particles can be both bosons and fermions. Okay, this is on this side. And we also said that, in fact, for mass larger than 1 keV, or if you want, for mass more than 1 keV, the dark matter cannot be produced thermally, because, okay, we discussed that if it's produced thermally and if it's a smaller mass, then it doesn't have enough time to redshift and to become non-relativistic basically at the time of structure formation and washing out fluctuations, and this therefore implies that the mass should be larger than this if it's thermal. Okay, so if we want to get a mass more than, for example, around 30 V, we need to find a non-thermal production mechanism, and this will be the misalignment mechanism, as we'll see in this lecture. Okay, then we said that if we go to occupation numbers smaller than so if you want to mass more than around 30 V, the occupation number is much larger than 1. The particles inside the W volume number of particles is much larger than 1. So all these W wavelengths will overlap with each other. And in this case, it turns out that the multi-particle state, the multi-particle wave function, solves the classical equation of motion, very well approximated by the classical equation of motion, which are the Klein-Gordon equation, or the Schrödinger equation is a non-relativistic limit. And the solution are classical free waves. So this is also known as wave dark matter, because basically the evolution is well approximated by classical wave. And then there are some wave interference effects. For instance, the fact that when these waves interfere, they make the effective field, the field at a certain point, for instance, in your detector, to lose its coherence, meaning initially is really a single cosine of time, but after the coherence time, which is around 10 to the 6 over m, two waves interfere, and the single cosine, the phase of the single cosine is lost. Okay. So, and then we also started introducing the motivation for introducing these particles with mass more than around 30 eV. Okay, I would be very loose, I would call this 30 actually 1 eV. These particles are introduced, are motivated because, in my opinion, one of the most interesting one is the QCD axiom that solves the strong state problem. So I told you that the strong state problem is the fact that in the QCD Lagrangian, there's in principle a term you can write that is gauge invariant, and it's called the theta term of the kind theta 0 G tilde. G tilde is a gluon, the dual group function. This alpha strong over 8 pi is some normalization factor. Okay, alpha strong, by the way, is G strong square over 4 pi, whatever. So this term violates CP. In fact, this coefficient theta 0 is actually not independent from the quark mass matrix, because you can show, and I'm not going to do it, I'm not actually going to do it, but you can show that in fact, by doing field definition of quarks that are of the kind e to the I alpha over 2 gamma 5 q, maybe with a minus sign, these field definitions change both the theta term and the phase of a quark mass matrix, because they are anomalous under UCD. And another result, what happens is in fact that only the combination theta 0 and the phase, that we call me alpha of the quark mass matrix here, the overall phase of quark mass matrix, they're fully division independent. Okay, and then we said that there's a bound on theta coming from the electric dipole moment of the neutron that is smaller than 10 to the minus 10. And this is a source of problem for us because we expect the dimensionless parameters of order 1 unless a symmetry is restored when its parameter is set to 0. A symmetry is restored in UCD, which is CP. However, CP is broken in the full standard model because of the phase of another phase in the U covers of the standard, which is basically the CKM phase. And as a result, we don't we think that this is a problem. Some people think it's not, but okay. This at least is a puzzle. And we would like to explain this problem dynamically. And if you want, the most robust solution we have is the so-called UCD axion. And the story goes as follows. So the UCD axion is a new scalar, is a scalar boson, that they call A of X. And the fact that I call it A of X would be a source of problems when I call also the scale factor A of X, scale factor of the universe. So and that it will be found at that point. So it's a scalar A of X that has the following property. By definition, so there is a pitch a U1 symmetry that they call Peche-Quinn symmetry. Okay, under which the axion changes as the axion itself plus alpha Fa. So alpha will be my parameter of this my U1 symmetry. So okay, is this parameter, is a constant parameter, and Fa is a high energy scale. Is a scale with a dimension 1 in mass, and it is a high energy scale. Is larger than about, okay, we will see later that it's larger than about 10 to the 7 and 10 to the 8 GeV. So this is a high energy scale. So this is my first definition, so the first point. The second point is that my Lagrangian, so the Lagrangian of the standard model plus QCD axion that they call L tot, under this transformation should just form like L tot goes to itself plus alpha strong over 8 pi GG tilde. So the statement, so QCD axion is a scalar field that transforms in this way under this Peche-Quinn transformation, and the Lagrangian is invariant basically under this transformation, except for this term alpha GG tilde. And this implies that in fact the axion Lagrangian, okay, the L tot will contain the following terms. So I have a half d mu axion square, no, plus something like alpha strong over 8 pi, A over Fa, GG tilde. So because if it is the case, no, under this transformation, this Lagrangian is invariant because the mu A doesn't transform because it's a derivative, and this alpha GT that produces this term. Okay, so this is the definition of UCD axion. Now I'm going to tell you why it solves the strong state problem. Let me tell you, however, that in principle I can add other terms here that preserves this shift symmetry. So this term look like the following. First of all, I have a coupling to photons that conventionally is written like 1/4 Ga gamma gamma FF tilde, where this is F mu nu, F tilde mu nu. F tilde is defined as the gluon field strength, but with the photons out of the gluon. Okay, and I have A over the Fa, of course. This term, okay, and then I can add other couplings, for instance, to the standard model quarks of the kind d mu A over the Fa. Then I have some over I, so all the quarks, Ci, Q bar I, gamma mu, gamma 5, Qi. So these terms clearly preserve the shift symmetry because the derivative. This term looks like it doesn't preserve it. However, turns out that FF tilde is a total derivative. And contrary to this one, in fact, preserve the shift symmetry because you can always rotate it away. And and the fundamental reason is that this one is not affected by something called QCD instantons, while this one is affected, and we will see later why it's the case. Anyway, so the idea is that this term and this term here are in fact shift symmetric, and the only term that breaks the shift symmetry is this one. So a few comments. First of all, you see that all the couplings of the axion to the standard model are suppressed by powers of FA. So FA, we will see, is a big scale. So FA is very weakly coupled to the axion is very weakly coupled to the standard model. And then this term looks like really the theta term, no? So if you want A over FA replaces my theta term in a standard model, it means that it's an effective theta term. And in fact, on paper, what I should do is also to write the standard model Lagrangian, which, okay, I should write also the quark Lagrangian that has something like Q bar, I slash Q, and so on. And my theta term, Gg tilde. And in practice, the A over Fa and the theta term are grouped together in the same coefficient in front of Gg tilde that I just call axiom. So from now on, what I call axiom will be A over Fa plus the theta term, because I can always do this filter definition to kind of throw away this theta term. Yeah. No, it's invariant except for this term. So the definition is that it's invariant except for this term. Okay, in principle, I should say, to be fair, that to solve the Sonsui problem, in fact, you can also have some very, very small breaking of the Pechet-Quinn symmetry. So you can have terms of the kind just purely terms that are non-derivative, like for the kind AFF, no, or A Q bar Q, the one that Sujit was mentioning today. The coefficients, however, need to be super small in order to be able to solve the Sonsui problem. So these coefficients need to be small. So you can have a small break-in, but this is small. Otherwise, I didn't tell you yet how you solve a Sonsui problem, but the idea, after I tell you how, you will understand that this coefficient need to be small to solve the Sonsui problem. So basically, you can have very small coupling to the, also non-derivative coupling if you want to the standard model. Okay, so why does this particle solve the Sonsui problem? This particle solves the problem because in fact the energies below. So now I go at energies below lambda QCD that I conventionally take 1 GeV. Okay. In particular, I'm going to look at the energy of the vacuum, and I claim that in fact in the vacuum, which is basically okay, in the vacuum with zero energy, so the expectation value of A over the Fa, if you want, is 0. And if it is the case, now I'm going to show you how. Then, of course, expectation value means that the theory solves the Sonsui problem dynamically, because this term effectively is not there in the vacuum. The price to pay is that I introduced a new field, which is the QCD axiom. Okay, which can you can detect in principle. And the reason for that is that in fact at energy below lambda QCD, this term here generates a potential for the axiom, an effective potential for the axiom. And how do you see that? Well, I'm not sure how many of you have done quantum field theory. Maybe all of you, almost. So in principle, you can calculate the effective action for the axiom theory, and in particular, you can calculate the effective potential. So the way you usually do it, you consider a field configuration, and you call a bar that is independent on space and time, because usually to calculate the potential, you consider a space and time independent configuration. No, that's what the potential is in the end. I consider this space time independent configuration, and then I I calculate, well, effective potential is basically defined to be e to the minus effective potential, that's called V of A. Okay, then I have the Euclidean for volume. This is equal to, if you want, the path integral over all the quarks and the gluons of e to the minus the action that I wrote here. So the integral over L d for x. And where here I done the quote unquote weak rotation into Euclidean space. So this is standard stuff. So this would be the main effective potential of the axiom. And this is why I have to compute the integral, which is impossible to do. Well, you actually have to do it numerically, or use techniques such as scalar perturbation theory. However, now I give you an argument of how this potential looks by calculating this path integral. And the idea is, okay, this will be L tot, calculated in this axiom configuration A bar. So when I calculate this L tot in this axiom configuration A bar, okay, and then of course I have also the quarks and gluons, and so on, d for x. What happens? Well, this goes to 0 because it's space-time independent. All this goes to 0. The only term that remains is this one because everything is derivative. So in practice, this stuff becomes something like the action of QCD, standard action of QCD, plus minus I integral a bar over FA, if you want, integral of GG tilde therefore x. Okay, this will QCD at theta equal to 0. Okay, this will be just q bar slash q plus just L1 square. And why there's an I here? Because if you go to a Euclidean space, this GG tilde d for x gets an I. Okay, this is because you're going to Euclidean space. Anyway, long story short, in principle you have to do this crazy path integral, and you cannot actually do it. You have to use Scalar perturbation theory techniques to do it precisely, or at least hope to do it precisely, or you have to start doing lattice QCD. But long story short, turns out that there exist field configurations where this G tilde integrating the x of G tilde is non-zero, and these are called the QCD instantons. So there exist field configurations where integral in the for x of G tilde, okay, modulo some normalization factor, which I'm not writing, this is non-zero. And in fact, if you require that the action of QCD is finite, okay, the action of QCD is finite, this integral is in fact an integer number. So this is an integer number n in Z. Okay, these are instantons or QCD instantons. Okay. So what happens? So of course the configuration with n equal to 0, which is basically a mu gluon field equal to 0, will not give me any contribution to this axiom potential because if I get a mu if I this equal to 0, there's no contribution because all the contribution will come from when this is non-zero. Turns out that as a first approximation, you can consider the first two that have n equal to plus or minus 1. And I'm not actually going to go into too much detail, but the idea is that the one given with plus 1 will give me e to the minus I a bar over FA. Okay, and the one with a minus 1 will give me one with a plus, plus e to the I a bar over FA. And then I have this e to the minus s QCD calculated in this configuration, which I don't write. And the sum of the two will give me a cosine, basically. So long story short, what happens is that right here is that v of a bar, which is in fact a function of a bar over FA, because in the end only a bar over FA enters. A bar over FA, is something of order minus lambda QCD to the fourth, which is basically the only scale in my problem, more or less, times the cosine of A bar over FA. Okay, this is the simplest way of getting to the formula. So I evaluate this path integral on these three configurations that have non-zero GG tilde, and they exist in QCD. Yes. There's an infinite number of them, because I want to simplify the story a lot. In fact, this integral is divergent. This integral is divergent, and it's not actually not well defined, because basically all of them contribute equally, and in the end, the calculation is not under control. But yeah, indeed, now, as we'll explain now, the potential is not this one, it's different from this one. But this is just a naive way of writing it. Okay, let me finish, then tell you what. Okay, but you see that, okay, there's a minus cosine, and that minus cosine is minimized at a equal to 0. So in the end, long story short, the potential for the axion, okay, very roughly, okay, V of A over F, A bar over, okay, A of A over FA as a function of A over FA looks like, well, something minimized at 0 and periodic. So here I have pi, okay, and here is 0. So it's finished. I proved that A over the FA is 0. As a result, the effective theta term is 0, and this solves the strong field problem. But here this is also okay. Then I have to tell you one thing. So this is periodic of period 2 pi FA. So instead A, okay, okay, this actually keeps to be a symmetry. So despite potential breaks, the shift symmetry, this discrete shift symmetry is still preserved. And then, okay, is minimized at 0. Okay, A over F equals to 0. And then is even. So A minus A, okay, is even. Okay. Then, as was pointed out, in fact, this calculation is actually wrong, because I have to sum over actually all the configurations, also with those with plus, also more instantons, and in fact I have to do the full saddle point approximation around all these configurations, which turns out that is to be actually divergent, because it is dominated by instantons on which you don't have control of the size, basically. So what people do to actually calculate the axion potential is not doing that calculation, but they use something called chiral perturbation theory, meaning that they use properties of axial anomaly to shift this this axion coupling into the quark mass term. And if you ever see chiral perturbation theory, quark mass terms can be encoded in chiral perturbation theory. I'm not going to give any detail about this, but I'm just going to say that if you do the proper calculation, the potential is in fact approximated by minus m pi square, f pi square. Okay, then I have square root of m up square plus m down square. These are the mass of the up, mass of the down, plus 2 m up, m down, cosine of a bar, okay, a over fa, and then I have m up plus m down. Okay, so this will be the leading order calculation in chiral perturbation theory of the axial potential. And you see that, of course, it's completely different from that result. So this is that one is wrong. So let me wrong. But as you see, the important properties that we needed are still there. No, so this will be a function that cannot different, but still is a okay. Maybe I show you like this. It's still a periodic function that is minimized as a equal to. So let me show you like that. So with my color perturbation is the correct one. So V wrong, and this is the correct. Okay. And I still minimize a equal to zero. Equal to zero. And in fact, you can show that these three properties are correct. In from a particular point of view. They are correct in a perturbative way. And I don't want to show that. Yes. Yeah, we know, but I don't have time to tell you. We No, here, okay, here is an the effective theory of QCD, color perturbation theory, is as exact as you can calculate properties of the pions, for instance, pion scattering, and so on. Here, there are collections proportional to something like a map over M strange or n down over M strange, which are small. Okay, these are collections of this kind, because I'm expanding. Okay, I don't want to say, but I'm expanding over small quark masses. But the collection, but still, even if you include the collection, you still minimize a equal to zero, because this is basically a property of the cube. So you see, somehow all these harmonics of my instant calculation kind of conspire together and give me this kind of crazy function, which is not a cosine. Anyway, this is not really the point of these lectures, but the idea is that we have a potential for this particle, potential coming from this term, and this potential, okay, it's a is effective at energies below lambda QCD. So I'm basically integrating out QCD and getting on this potential. Okay. Yeah, you get some, but mu is not MD. So there are some properties if mu. It's wrong. It's wrong. You have to sum. The calculation is wrong. The instant calculation is wrong. Not so wrong, but well, as you say, I didn't actually compute the coefficient in front of I just taking the theta dependence. No, I say okay, there's a cosine because I have e to the I plus e to the minus I. But if you actually calculate the coefficient in front, you're not gonna get stuff that makes sense, because you get something divergent, because it turns out that path integral is in fact divergent, because you basically integrate over all the instanton sizes, and those that are big, the instantons that are big in size, okay, lead to a divergent okay, basically infinite coupling, so a diversion action. So the calculation you cannot do it. You cannot do it at finite temperature when instead the QCD is perturbative. So where the gauge coupling is small. But I don't want to spend too much time on this. The only thing that we want to say that there's a potential that is minimized at a equal to zero, and this solves the strong state problem. And also you get a mass v second at zero. This will be the mass square, which is basically m pi square, f pi square over f a square times m up, m down, divided by m up plus m down square. So there's a mass. It's a mass proportional to the inverse of the action delay constant. A mass, if you plug in the numbers, this mass is 5.7 times 10 to the minus 6 EV for 10 to 12 GV over the phase. So for a phase that are not ruled out, as we'll see later, this mass is very small. So this QCD action, if it's the dark matter, it's in our wave-like regime. So we have a motivation for a particle beyond standard model that is light, basically coming from solving a problem of a standard model that we think it's a problem with a standard model. Okay, this all I want to say about positive motivation for the QCD action. But I need to tell you another thing regarding some UV completion of this particle. Questions? Yes. What's that? This one? This one because well, this one because it's in principle a total derivative, and so the naive argument is that you don't have these QCD instantons for this for this f this for this f the photon, because the QCD instanton are related to the properties of gluons, first by the structure of the SU3 group. It's like these are maps from the space at infinity to SU2, which is a subset of SU3, and these maps don't arise for this FF tilde. So this term doesn't really contribute. Okay, this is a property of the instantons. Okay. Also, this term in practice, okay, yeah, this term yeah, it doesn't contribute because of that reason. Yeah, this term doesn't, yeah. Another way to see is that if I put a constant A, if I put a constant A, I put there a constant A, this FFT is a total derivative, which okay, which I can actually reabsorb via a Carat transformation that I didn't have time to show you. That is, for instance, a combination of baryon and lepton number. Okay, it turns out the combination of baryon lepton numbers allow me to redefine away these all the couplings of the kind WW tilde and okay, BB tilde. These are the gauge bosons of the SU2. Turns out that you're doing a baryon or lepton number transformation combination of the two. These are chiral, and they allow me to change the coefficients of these and put them to 0, and they're still symmetry of the standard model. Okay, so this is another argument of why you can neglect this. But okay, the standard argument is that this leads to instantons. This one doesn't, because the properties of the U1 group with respect to SU3. Okay. I can tell you more in detail, but this is not actually the topic of these lectures, because, yeah. Plug the numbers. Like, I need to plug the numbers for m pi. I mean, just put m pi 135, g mev. F pi is 90, and m up is 2 mev, and m down is 4 or 5 mev. And you get this number. Sorry? How do you get the relation? Via Cadet perturbation theory that I'm not gonna tell, because otherwise we're not gonna talk about dark matter. Well, unless you don't want to know about dark matter. Okay, just want to say that, okay, there's this particle, the Einstein model, that has that potential. I didn't show you how you derive it. You have to trust me that it's like that, or we can discuss afterwards. And since I'm gonna need it for a specific cosmological scenario, I will have to tell you a model where this axiom appears. So as you see, as the energies become larger than Fa, since it's the dimension 5 term, this theory is strongly coupled, meaning that it needs to be UV completed. So I need to UV complete the QC axiom theory in some way. And there are several ways to do it, but all these methods to UV complete the axiom theory into basically a normalizable Lagrangian are based on the fact that basically I need to reproduce these shifts, the shift symmetry, except for the GG tilde term. So I have to basically have a theory that is invariant under shift symmetry, except for this GG tilde term. In particular, it turns out that these theories have a U1 symmetry, okay, symmetry, that is spontaneously broken at a scale of order of Fa, okay, and all these theories, in addition, for this theory, the symmetry is actually also anomalous. Okay, under SU3 color. So this U1. So all the theories that basically UV complete the axion will have a U1 symmetry, Peche-Queen, called Peche-Queen, that is spontaneously broken in scale FA. Since it's spontaneously broken, then you get a Gaussian boson that is basically the axion itself, and it's anomalous on SU2 color. And this anomaly, in fact, this anomalous will reproduce, if you want, that alpha strong G tilde, okay, or A over FA G tilde term. So these are basically the two generic ingredients that you need in a UV theory for reproducing that low energy Lagrangian. And this is almost a theorem, okay. And so in the end, what one needs to do is to basically add the new fermions or add new scalars or new particles in such a way that you recover a U1 symmetry that is anomalous on a QCD. In the standard model, there is not, because visually there's this axial symmetry that I wrote before. However, it is not actually a symmetry because the mass of the up and the down are non-zero. However, the idea is that you have to introduce new scalars and new fermions to have a symmetry, and possibly these fermions should be charged under a transformation to reproduce the anomaly. So I'm just going to tell you a simple model. It's called KSVZ model that I need later to discuss the cosmology of one scenario. So this KSVZ model works like as follows. So this KSVZ is called from Kim, Schiffman, Weinstein, and Zakharov, I think. I don't want to misspell people. Yeah. And the idea is that, well, I need to, first of all, have an anomalous symmetry under QCD. So I have to have a new quarks. These are heavy quarks. Okay. Okay, that are in a fundamental, okay, fundamental of SU3 color. These are heavy because since they're fundamental, they cannot be light because they will be ruled out. So these are okay. And the quarks basically should transform under the Peche-Queen symmetry, okay, under this U1 symmetry, as basically quark e to the minus I alpha over 2 gamma 5 q. Okay, and as you know, maybe from quantum field theory, this symmetry this transformation is anomalous, so changes the path integral measure via that alpha G tilde term. Because there's a gamma 5. Okay, these quarks need to have a mass. However, I cannot just put a mass term by hand. No, because if I put the mass term by hand, the mass term will break this symmetry. So to do that, I also introduce a new scalar that I call phi, which is a singlet of standard model. Standard model singlet. So in Lagrangian, if you want, would be okay SVZ. Okay, this scalar will basically couple to the quarks, and will have a VEV in such a way that I get the a mass term via corresponding Higgs mechanism. So in other words, the Lagrangian is let me write in a concise way: Q bar I slash Q. These are the kinetic term of the quarks. Then I have the kinetic term of the new scalar, pi modulo square. No. Then I have a potential for the scalar, phi modulo square minus v square over 2. This looks like very much like the standard model, except for the fact this is a complex scalar and not a doublet. Okay. Plus a Yukawa term, y, phi, q bar left, q right, plus cc. Okay. So the scalar has a potential that breaks, okay, that has a VEV. So in the vacuum, phi is equal to v over 2 through root 2, which is non-zero. Okay, so because it's potential. And then you see I put a Yukawa interaction, and in order for the theory to be invariant under this Peche-Queen symmetry, I have to ask that the scalar transforms as e to the I alpha q phi, sorry. Because if I do that, then this q bar left, q right, okay, we transform, okay, q right transforms like e to the minus I alpha over 2, no? And this transforms also as e to the minus I alpha over 2, because this gamma 5 transforms q left and q right in a different way. So q bar right transforms like q left, okay. And then this transforms to e to the alpha over 2, e to the alpha, so they cancel basically. So this means invariant under the Peche-Queen. So long story short, I managed to write a theory with this transformation that is anomalous on the QCD, and okay, by introducing new fermions and a new scalar. And importantly, now this 5 gets a VEV, and while getting a VEV, it creates a mass, an effective mass for the fermions, no? Because as you probably know from a standard model, if a scalar gets a VEV, you get a mass from the fermions. And in particular, the mass. So let me write the degrees of freedom. So the scalar gets a VEV. So I write the scalar as r of x. So phi of x. I write r of x plus v root of 2 e to the I r a over v. So this v is a parameter of my choice. This is a invisible high energy scale of my choice. Okay. And similar as you do in the standard model, you write this complex scalar as a phase plus times a radial mode. This we call a radial mode. Radial mode. Okay. And A will be related to the axion, as we would see. This is the Goldstone boson of this U1 symmetry that is spontaneously broken. So long story short, this model will give me, as the degrees of freedom, this radial mode, no, 1. Another degrees of freedom will be the heavy quark, no, and a third degrees of freedom will be the axion, no. So the quark has mass. What is the mass of the quark in terms of y and v? What is the mass of some other quarks? Yeah, yv modulo some factor, maybe it's root of 2. A is massless at this level because it's the Goldstone boson of the U1 symmetry. There's no key, okay. And R also has a mass, which is the Higgs mass, which I'm not gonna, okay, so it will be MQ, MA, and MR. Okay, let me just write it like this. MR will be square root of lambda modulo some factors times V. No? This comes from this. Okay. And nothing. So in principle, what I have to do to match this theory with my QC axion Lagrangian, which I didn't delete. I was smart. I didn't delete. So what I have to do is I have to integrate out these two heavy degrees of freedom, because okay, this is a UV theory. I want to match this with a IR theory. Energies below the minimum, if you want, between MR and MQ. Okay. And so I'm not going to do any calculation, but the idea is that as I integrate out these degrees of freedom, I get some anomalous diagrams, in particular of the kind, let's say, gluon, and then I have my heavy quarks, Q left, Q right, coupled to the axion. Okay, so this coupling to gluons is because these quarks are charged under SU3 color. No, this is from the slash there. So this is the G strong, no, and this comes from the Yukawa there, right? So once I do this calculation, which I'm actually not going to do because I don't have time, and also because we're already very late, uh, I get that basically that I get a coupling of the kind of this kind, but on the other hand, instead of getting exactly FA, I get V. I get V there. So I get so in the end, the IR Lagrangian will contain a half the A, the mu A square. No, this comes from the kinetic term of this phi, written in terms of this A. And then I have alpha strong over 8 pi, A over V, GG tilde, and this comes from this anomalous diagram. And then I don't have anything else. Okay, the same principle, I have more operators that are suppressed by higher powers of a Fay that I'm not gonna write. The higher operators over of V. Sorry, so there's another. Okay, this okay. Anyway, long story short, this Lagrangian, this theory reproduces the QCD axiom with Fa equal to V. Okay, and this is called the KSVZ model. So I have a model, you understand, a model where I can actually reproduce the QCD axiom, which is UV. Okay. Yes. No. Well, what do you mean? The anomaly is, I mean, it's defined like this. I mean, what is the anomaly coefficient of a UV quark? Ah, yeah, of course. Yeah, but okay, but then I can redefine, so whatever I get D here, I can redefine to be, so because if I get something, now we will see what happens, but if you get something here, you can redefine to be, but so in fact, now I wanted to say that if you suppose that now instead of having one quark, one of this Q, you have N. So instead of having Q, you have Q1, Qn. I have N of them. No, I can have N of them. All the same properties, they are fundamental of SU3 and so on, all the same thing. So in that case, I can do this game n times. So I get n times that diagram. So in the end, if I have n, here I have a n here, because I can do the same game n times. And in the end, my effective FA will not be V, but will be V over n. So in general, FA will be important formula V over n, where n is the number of quarks in the fundamental representation of this okay, of SU3 color that are charged under the Pichet-Queen transformation. So this will be if I have n quarks. Yes. So FA for me is a coupling that stays in front of GG tilde in the IR theory, in the theory where I have integrate out everything. Well, V is a scale of Pichet-Queen symmetry breaking that is related to FA via some probably order one factor. Okay, that's. And indeed, now I was telling that I was about to say that it might be that indeed these quarks, these quarks in the fundamental SU3 color can be in fact also in the fundamental or in a sample representation of the electromagnetic. No, it can be U1 or some representation of U1 electromagnetism. Okay, mean that a charge on the electromagnetism. So in that case, what happens? I have this diagram, but I also have the corresponding diagram where I have a photon, and quarks, Q left, Q right, and then I have the axiom, no? And this is proportional to electromagnetic charge. And this vertex comes from the fact that I have added this quark that are charged also on the, okay, this also are charged also on electromagnetism. If you calculate the diagram, the diagram in the end leads also to a coupling of the axiom to uh, to basically photons, no? F mu nu, F tilde mu nu. Okay, and this coupling is historically parameterized in the following way. Is historically parameterized as alpha electromagnetic over 8 pi, okay, 8 pi. Okay, and then I have some E over, okay, E over N. So what am I doing here? So this what is V, no, is the same as this V here. And this E is defined to be something like twice the sum over I of the Pechequin charge of the quarks, I, and the electromagnetic charge square of a quark I. So this is just a complicated notation to say that, okay, these quarks are not electromagnetic charge, I get 0. Then if they are electromagnetic charge, I have to put the charge square because I have twice there. And then if they also need to be charged under Pechequin, so I have to put the Pechequin. So this usually is written as the trace of Q Pechequin Q electromagnetic square. So there's a trace, like this is basically a trace of the same thing. And the two comes from the fact that the normalization of the of the generators of U1 is a factor of 2 different compared to SUN. Okay, that's the reason. So long story short, I expect that I have an effective, in general, I expect to have an effective axion Lagrangian with these two couplings, where the corresponding coupling of the, yeah. This one? When do I get it? Well, you can compute it well, the action doesn't exist. Well, the action doesn't exist now before the symmetry breaking. So, I mean, the diagram makes sense only after now because the action doesn't exist. Well, yeah. Yeah, you got that diagram. Okay, but there's an easier way to see how it occurs, but I don't have time to say it now because I actually want to talk about dark matter. This just to put everybody on the same page, saying that indeed you expect these couplings. And then the last thing I want to say before going to cosmology, so is the fact that usually this E over N is okay. E over N is clearly can be very easily 0, no? Because if the quarks are not charged in electromagnetism, I get 0. But in some motivated models, E over N is equal to 8/3, because this 8/3 basically is a complete representation of SU5. Okay, if they stay in a complete representation of SU5, then you get 8/3. And it's also the case of the so-called DFSZ model. So, and why that's why usually in plots you see this with Q electromagnetic equal to 0. Okay, you see these two terms because these two values because you have these two possibilities. But okay, of course, is a free parameter. You can choose it as you wish. And then last thing before going to cosmology is the fact that when you actually try to detect the axion, okay, so you actually, so now let me go here. Okay, maybe we go here. You studied the theory energy below lambda QCD. So you usually you don't have this term. Okay, because you study it. So in principle you have quote unquote integrate out QCD. And basically when you integrate quote unquote integrate out QCD, what happens is that the axion gets a mixing, so I have an axion, gets a mixing with the pion via this term, no? So via that term, the axion gets a mixing with the pion. The pion, as you might know, couples to the photons via the so-called Wino-Witten term, okay? you might imagine there's a cupping of the pion to the photon of the kind pi over f pi times ff tilde. This comes on the E1 anomaly with respect to electromagnetism. Okay, if you never saw it, never mind. But the idea is that given this mixing, in the end, the axion gets another contribution. The axion capital photo gets another contribution on top of this one. That basically comes from the mixing with the pion. And if you compute it, okay, the contribution is such that, okay, this G gamma, okay, at energy is below, okay, at energy is below lambda QCD. This G gamma gamma is given by the term I told you before. No, this okay, alpha electromagnetic over 4 pi times E over n. This term I told you before. That term there. And then I have this contribution mixing with pi, which is a number that you can calculate is 1.92 with an error of 4. Okay. Okay. This is 1.92 with an error of 4. Okay. And long story short, that's why you see usually these formulas in plots. No, you see these formulas because you have also so in principle with E over n equal to 8/3, there's a small cancellation. Okay, and I'm done. So you see the axion capital to the photons proportional to A over f A, no? And this is why usually in plot you see the axion plot with respect to the photocupping going up. So what you usually see is the following plot that was shown many times in previous lectures. You see this plot where you have this Ga gamma gamma proportional to Ma. So Ga gamma gamma, okay, this is capital photon. Well, let me put the Fa if you want here. Okay, Ga gamma gamma would be Ga gamma gamma for the QCD axion is proportional to 1 over Fa. But as I told you before, it's also this was proportional to Ma, no? And in the end, you get a plot of this kind, no? Where usually these two choices occur for E over n equal to 0, E over n equal to 8/3, where the second is smaller than the first one, because for the second you have a partial cancellation between these two contributions. Okay. 9.2 is some combination of mass of the quarks and the charges of the quarks that I'm not going to tell you because I want to talk about cosmology. This coupling is model independent. This coupling is model dependent because it depends on the charges of these quarks that are charged on the Peche queen. This one you can have a cancellation between the two. You can, first of all, you can play a lot in such a way that this number is equal to this one with some sort of fine tuning or some model building, and people have done them. And now it's called photophobic axions. I think you can build models where the two cancel with it in principle, or you can have a more in principle you can do it, but with enough. But normally with this model, no. Okay, you have to play a lot with the numbers. Okay. By the way, so this is a plot. So usually you will see bounds here coming from something called helioscopes. Okay, this corresponds to G gamma gamma around 10 to the minus 10 over GV. No. Okay, then another bounds here for the mass starting around, let's say, 1 eV. And these bounds come from basically decay of the axion because it becomes unstable. Okay, I've introduced this particle just to say this particle is stable cosmologically because you can compute the decay of this particle into photons. Decay rate is proportional to 1 over it's proportional to G gamma gamma. Okay, this decay occurs in this way. These are photons and this is the axion modulo square. It needs to be proportional to G gamma gamma square. So I have G gamma gamma, square, and then everything else, the only other mass dimension I have is the mass. So this G gamma gamma square is Fa to the minus 2. So I have to put the axion mass cube to have the correct dimensions. And this is much larger than age of the universe, for basically Fa larger than around 10 to the 5 GV. So the axion is completely stable for the values of Fa that we are interested in. Okay, and this 10 to the 10 GV corresponds, let's say, to Fa 10 to the 8, 10 to the 7, 10 to the 8 GV. Okay. And I'm done. Okay, then in principle I can do a generalization of the axion that is called axion-like particle. And I'm not going to say anything about this, but except for the axion-like particle is an axion, but not of a universe or of a world, but of another world. Meaning that I have the same thing, but for a gauge group that is not is confining, but it's not the QCD one. So I can imagine there's a dark sector with an SUN gauge group, and I have a U1 symmetry. So I have I have a U1 symmetry that they call generalized Pechenquin symmetry. So it's called ALP. I have a generalized U1 Pechenquin symmetry that is spontaneously broken, at some scale that is still called Fa, okay, and also anomalous under some dark gauge group. So I have SUN dark or whatever. Okay, there's a dark gauge group G dark, and because of similar couplings of the axion to because it's anomalous. Okay, you get the same physics, except for the fact that now the potential has one more free parameter, no? Because potential will be of the kind minus lambda dark to the fourth times the cosine of A over Fa. But lambda dark now for me is a free parameter because I can play with dark stuff. I cannot play with standard model. So for me, the ALP mass would be something like lambda dark square over the Fa. The ALP also lies in string theory where they get masses via different effects. And importantly, for the ALPs, I can actually write more of these terms because the ALPs don't really couple to the standard model. Well, they don't have to solve the Sonsori problem. In fact, these ALPs do not solve the Sonsori problem because they don't couple to QCD like the QCD axion. And they can have more CP violating interactions or like Pechenquin breaking interactions, like this one. Okay, this is for me what is an ALP. So it's the QCD axion, but for a new sector where basically I can have a freedom choosing the mass with respect to the decay constant. So because I have a new free parameter. So for the QCD axion, the mass decay constant related to each other via formula that deleted is 5.7 10 to minus 6 EV for Fa 10 to the 12 GeV. But for this one is completely free. I can choose lambda dark. Final thing is that I want to know. So now we go to the actual universe. Actual universe as the evolution of the universe happens at finite temperature, as you might know from Francesco's lectures. It happens at finite temperature, so in principle I have to calculate the axion mass at finite temperature, which I will not do, but it's possible. And long story short, it turns out that at finite temperature, in particular temperature larger than lambda QCD, the QCD becomes weakly coupled because at higher energy, as you may know, QCD becomes perturbative, and you expect that given I deleted exactly the thing I needed, but okay. The idea is that given that there is alpha strong here, when alpha strong goes to 0, so finite temperature, let's say at much larger than lambda QCD, alpha strong goes to 0. So you expect that there is no the effect of this term goes to 0. In particular, that the axion mass comes from that term, you expect the axion mass going to 0. So you expect that the axion mass, QCD axion, goes to 0. And I'm not going to tell you any detail, but the idea is that I can plot the axion mass, MA, as a function of temperature, Okay. And there's a critical temperature that we call T critical, which is basically where the QCD phase transition happens when the quarks go from basically current condensate to where the current condensate of quarks goes to zero if you want. The quarks don't condense anymore, which is around 150 G MeV, such that for temperatures below this, the axion mass is basically equal to its zero temperature value, Ma 0, which is the value I told you before, no? M pi square, F pi square, wave a square, blah, blah, blah. A large temperature, however, the mass goes to zero, and goes to zero with a power that is temperature to the minus alpha. And it turns out that the alpha is around 8. And in fact, at finite temperature, the instant calculation I told you before is valid, turns out to be valid. And in fact, the potential of the axion looks like almost exactly minus ma square of t fa square times the cosine of a over fa. And the argument of why it's actually valid at finite temperature is that it turns out that higher and higher instant contributions become suppressed with the powers of the coupling, because as you probably have seen in one of the previous equations, with if I increase these higher instant contributions were also accompanied by higher powers of the coupling, if you want, and so they're more and more suppressed as the temperature increase. Anyway, so this is the more or less the result of finite temperature. So we will see that the evolution of the axion will happen in a regime where the temperature is actually much larger than 150 MeV. The cosmological evolution will happen here, no? And as a result, we will probably need to utilize this temperature dependence. Final thing, for the ALP, instead, MA is not a function of temperature, because, okay, in principle, the ALP is a dark sector, and if I believe that this dark sector is not entirely equivalent with a standard model, or is not entirely equivalent with self, it's a good approximation to assume that it's not for the ALP. This is not a function of temperature. However, I can build, of course, models where I have a dark sector which has a heat, and then I can also have some dependence on that. But for the ALP, I will assume temperature independence. And I'm done with the axion. I'm half an hour late. But questions? What's that? 4, not 8? No, this because I meant mass square. I meant mass square. Sorry. And also I will parameterize just to say ma square of t, okay, or ma of t, like lambda square, which is lambda QCD over Fa for temperature that are, okay, then I have lambda over t to the alpha, okay, it's like put alpha over 2 for temperature larger than Tc, okay, or simply lambda square over Fa for temperatures more than Tc. Okay, this basically I'm just parameterizing this power law in this way. So this is what I will do. Okay. So now we are ready, all the ingredients to understand what is the evolution of this particle in the early universe and see finally this Mizrahi mechanism. And the idea is that the axion has this potential I told you before, sort of cosine potential that is actually a cosine at very high temperatures. And it turns out that in the early universe, it might be that the axion is in fact, as an initial condition, not at the minimum. In particular, it can be misaligned, quote unquote, with respect to the minimum being equal to 0. It can be at a certain position, and during the evolution of the universe, the field will feel a force that will bring the field to minimum, and the corresponding oscillations of the axion minimum will behave like cold dark matter, and this is called the Mizrahi mechanism. Okay, and now I will explain to you in detail how this works. Okay, so let's go to part 3, which is misalignment mechanism. Okay, I'm trying to keep my organization. So, I don't want to spend too much time on cosmology because you already saw more or less this stuff with Francesco, misalignment. But alignment. But the idea is that the universe expands. So if I have a box, the box expands over time. It expands, so two points, no, become far apart from each other, go far apart from each other, and the expansion is usually parameterized via scale factor. That, as you see, I have a problem in calling A because A is also the axion. So what I'm going to do, I call it R, ROT. This is a notation that will hunt us in the following, but okay. This is called scale factor. Okay. The scale factor is independent, and its standard derivative is positive, so means that the universe expands. So the rate of expansion is given by the Hubble parameter h of t, which is r dot over r of t. And the Hubble parameter basically represents also basically the size of the universe we can see, more or less, because it's basically the inverse time that a photon can travel from the beginning of time. So I will call this actual parameter sometimes this other parameter sometimes also the size of observable universe. So you can think that the observable universe will have size more or less 1 over h. So the time of the typical size of the universe we can observe, the inverse of the other parameter. Then I'm not going to say much. I'm just going to say that in the denomination, okay, the evolution of the other parameter is determined by the content of the energy content of our universe, and this is given by something like 8 pi g over 3 times rho. Okay, this is the energy density of our universe, and rho in the radiation domination is proportional to the temperature of the radiation bath to the fourth. So many times in the radiation domination I will approximate h like t squared over m Planck. Okay, here I'm neglecting the number of degrees of freedom that are in thermal equilibrium because I'm lazy and I don't want to keep too many details. But this is what happens in the radiation domination. Okay, then I'm going to tell you that how does the evolution of the universe, so how do different matter components redshift? So you know how matter and radiation redshift, because probably you have seen in previous course, but matter redshifts non-relativistically, meaning that its density increases with the volume. So let me just summarize the fact that if I have non-relativistic matter, okay, we have a Q with some particles. As the universe expands, no, this Q becomes larger, no, and it's the number density of particles proportional to 1 over scale factor cube, and also the energy density of the particles goes like 1 over scale factor cube, because okay, assuming that the mass is constant, this stuff you know, right? And radiation, so relativistic matter, okay, which is also radiation. So if the number of quote unquote radiation particle is constant, okay, the number density goes still like 1 over r cube. On the other hand, you also know that the wavelength redshift, so momenta also proportional to 1 over r, the physical momenta proportional to 1 over r, and therefore the energy, which is basically momentum times the number density, okay, oops, it goes like to the fourth. And then we have the cosmological constant, where I basically a box of nothing, And its energy density, how does it redshift? It doesn't do anything. So energy density goes to R to the 0. And this is what happens to vacuum energy. So if I increase space, it's always vacuum energy because I have all these fluctuations up and down of my particles. If I increase my space, still I have fluctuations everywhere. The problem is that these fluctuations are not, I've decided we don't expect, much larger than what we expect, and this cosmological constant problem. Okay. So let me give us a brief history of our universe that will be useful for discussion. So our universe was once, in fact, in thermal equilibrium, was radiation dominated. So imagine that everybody was in thermal equilibrium. We were not like here. So everything was in thermal equilibrium. Then turns out that at some point radiation stopped dominating and matter started dominating. And then we're now in a period of domination of cosmological constant. So here I show scale factor, a function of time. Here I have RT0 today, which is usually 1. So what happened in the universe? Here I'm showing cosmological constant, the energy density. So at some point, the universe was dominated by radiation, where the energy went to like R2 minus 4. So at some point that occurred some billions of years ago, the matter started dominating over the radiation with this is matter with energy density goes to like R2 minus 3. And then close to today, in fact, we're dominated by some form of dark energy, cosmological constant. And this transition between matter and radiation occurs when the scale factor with respect to today is around 1 over 3300, okay, 1 over 3000, okay. There's a transition between matter and radiation called, it is called matter radiation equality. Okay, and this is actually very close to today. It's something like redshift, if you know what it is, 0.7. So not sort of when a bit before the dinosaurs died, but okay, maybe much before, but it's not that far. So just to say, just to have everybody on the same page, how do the different okay, let me write it here. So during radiation, okay, this is R to the 1/2. The scale factor goes like t to the 1/2. This is t is cosmic time now. During matter goes like t to the 2/3. This is obtained by solving the Friedmann equations that probably you saw at some point. And during cosmological constant domination, scale factor is in fact growing exponentially with time, with some constant h naught that is related to the cosmological constant, to the energy density of the universe that is constant. Okay, this h naught is a constant in your Hamiltonian if you want. And the other parameter, okay, you can do the derivative. It goes like 1 over 2t. Here goes like 3 over 2t. And here is constant, this constant h naught. Okay. So importantly, in radiation and matter domination, the other parameter, the corresponding horizon, grows faster than the scale factor itself. No? So because the horizon is proportional to t. No? T to 1 over 2t, okay, it's proportional to t, where the scale factor goes like t to the 1/2 or t to the 2 over 3, which is smaller than t. So it means that the stuff is going far apart from us, but at least we can see more and more stuff as the universe expands now, because the other parameter is increasing faster. The inverse other parameter is increasing faster than the scale factor, which is not the case during cosmological constant domination, where instead the Hubble parameter is increasing much faster with respect to the. Okay, the scale factor is decreasing much faster with respect to the other parameter. So here, if you want, the scale factor is increasing, but the Hubble parameter is increasing faster. Okay. Okay, so we can see more stuff. It's not the case today. Today, in fact, we see less and less stuff because we are in a period of cosmological constant domination. Okay, what happens before radiation domination? What happens? Well, before radiation domination, we don't really know because, in fact, we only know what happens basically at, for sure, at temperatures around 1 MeV, because we're indirect evidence from BBN, weak synthesis. We don't really know what happens before, but we are confident that there's a period of inflation. We're not confident, but most of us think there's a period of inflation, basically of cosmological constant domination. So at a certain point here, the universe was dominated by a cosmological constant, okay, where basically the scale factor increased like e to the h inflation times t, okay? This is called inflation. And why is this so? Well, you learn maybe in course. Why do you have inflation? Why would you ask for inflation? There's a horizon problem and flatness problem. And I'm not going to tell you what these are because we don't have time. But the idea is that, okay, maybe I can just say, where a problem, we're looking at the sky, no? We look at the sky in different directions, and we see that the photons have the same temperature, which is not possible, no? If I look at the universe in that direction and in this other direction, they're basically the same temperature. But if we assume that there's only radiation domination and matter domination, there wouldn't be enough time from the beginning of time, which is t equal to 0, for these things to be in thermal equilibrium. And so I need a period of exponential expansion of the universe such that these two points were in fact initially in causal contact. So maybe it's like a standard textbook story that you're probably not going to learn from me, but it's the fact that, okay, here is t equal to 1, t equal to t0. Here is when the CMB photons have been decoupled from electrons or whatever, and so we see two different directions in the sky. These two photons could have never been in thermal equilibrium, but if you have inflation, then these 2 points in fact correspond to the same point that was in fact in causal contact. Okay, during inflation, what happens? The universe expands exponentially, and all the fields that are lighter than the Hubble parameter due to inflation get exponentially stretched. Okay. Okay. So all the gradients go to 0. All the gradients of the fields go to 0, and also and also the temporal gradient goes to 0. In particular, you can think of a generic field configuration of the axion before the beginning of inflation in the following way. So here I have the axion, let's say over the phi, before the beginning of inflation as a function. Okay, so here you have x, you have axion over the phi. Before the beginning of inflation, the axion will have some distribution. Okay, it's some functional distribution like this, and that's probably between pi and minus pi, with some random distribution, which we don't know because it depends basically on it's an unknown. The distribution is an unknown parameter. It is an unknown distribution, and I go from minus pi to plus pi because the action is a periodic potential is basically a periodic variable, so it doesn't really mean, it doesn't make sense. So if I go more than pi, it actually means that I go in this direction, no? So because it's a periodic field. So what happens during inflation? So during inflation, all these points here, this point here, this point here, and this point here, get stretched. The physical distance gets stretched exponentially. So the physical distances go to themselves times e to the h inflation over t, where t the time of inflation. Okay, so what means that distances that were initially very small, they become basically super horizon size. So these points become, if you want, horizon size. This microscopic distance become horizon size distances much larger than distances actually that are much larger than h inflation. So in the end, the field will get a unique value in each Hubble patch that is different, if you want, in different Hubble patches. And this unique value, if you want, okay, let me see if I can, okay, it doesn't really matter. But this unique value, if you want, is set basically by chance, no? Because we could find ourselves in this point. We could also find ourselves in these other points, and we really don't know. So in the end, our universe will be a sub patch of this big patch. No, our universe. So we are here. No, it's a sub patch of this big patch, and in principle, the axion field after the end of inflation will have an initial value that I call A0. No, A0 initial value in our Hubble patch. It's like also parameterized like theta 0 times FA. Not to be this theta 0 not to be confused with the theta 0 I was initially. But this A0 is uncalculable, no? Because in our universe it can be some value, maybe 0.1.2 FA. In some other universe can be another value, for instance, very close to 0, for instance, just by chance. And this is uncalculable. It's one of the cosmographical properties of our multiverse. And so it's a good approximation, therefore, to assume that we are in one of these patches. It's a good thing to assume one of these patches where the insect was homogeneous, and therefore to solve the equations of motion of the axion, throwing away all the gradients. So in the end, I will assume that the axion will start in our Hubble patch with this value, and I will solve the equation of motion of the axion as the universe evolves. And just want to write them down, and then we will solve them tomorrow. Just 1 second. But the evolution the equation of motion are the same as we did in the first lecture. The equation of motion are basically those of a free scalar field, but in an expanding universe, and they are of the kind a dot dot plus 3h a dot minus the Laplacian of a over r square plus, okay, ma transform temperature times a equal to 0, where this is an approximation that the potential is in fact only the quadratic part. We will discuss better this tomorrow. Okay, so this is basically an harmonic oscillator, where this one I can put to 0 because I said before I'm neglecting all the spatial gradients because the field has been stretched out. This is an harmonic oscillator with a friction term, and this will in the oscillation that will come out will become a dark matter. Okay, and I'm done for today. Thank you. Questions? Everybody's tired. What is the relation? Well, the inflaton field is what drives this exponential expansion. The axion field is a spectator. So I'm thinking in the back of my mind that my Lagrange will have the inflaton potential for the inflaton Lagrange, that's the kinetic dynamo of the inflaton plus the inflaton potential plus an axion that is decoupled from the inflaton. So the inflaton drives inflation. It stretches all what contributes most to the energy density of the universe during inflation. And the axion is a spectator, so it gets stretched, like the fluctuations get stretched. So it's not the inflaton. Okay. Questions? Yeah. Yeah, tomorrow. Yeah. The Lake density is set by by the fact that I have to solve that equation. At a certain point, the axiom will start oscillating, and these oscillations, we calculated precisely what is the value of the Lake density as a function of a phi and theta zero. It's a number that we calculate, and is of the order of the observed dark matter abundance, in fact. Nobody? Yeah. So here I'm assuming that my initial condition is in fact close to the minimum. So here the correct thing would be minus v plus v prime of a over the phi, whatever, dA a over the phi. So this is a good approximation if your A0 is close to the minimum. So if you want the quadratic approximation is correct, in most of the cases this is the case. But if for some reason your theta 0 is over pi, so you are in fact in a patch where by chance you have 2 pi, then this quadratic approximation doesn't work, and if there is time, probably there won't be time, you see that these corresponding oscillations of the axion are delayed, because intuitively, if you're on the top, nothing happens. Like if you're on the top, you cannot go down. You just it's a cosine. It's on the top. Nothing happens. But if you're a bit far from the top, but not too far, then you have non-linearity that happen. This delay the oscillation and increase the dark matter abundance. Okay, but we will see this tomorrow. Yeah. No, that one was to calculate the effective axion potential. Because to calculate potential, I have to calculate the effective action in a constant field configuration, no? Because potential is basically you calculate the effective action where you throw away all the derivatives. To that, I have to put x equal to a of xt, no? A val without x and t, no? This this a quantum field calculation is nothing related to this one, no? So this is a number. Yeah, it's a uniform and time-independent field. But this is to calculate the axion potential via this instant calculation. It's nothing related to this stuff. So because when you calculate effective potentials in quantum field theory, usually consider, maybe people usually write a zero. I don't know. When they use a zero it's a constant field. Okay.